Lesson 6.3, Calculus BC, Definite Integrals and Antiderivatives. So, last two lessons been working out what this definite integral thing is. It has properties, the definite integral does. And the question is, what's the difference between if I do 0 to pi this way from 0 to pi, or if I do it the other way? To which you would say, in terms of area, there is no difference. But if we're talking about the integral, not the area, the answer is that here we get 1. Here we get -1. Try it on your calculator if you want. Pause the recording. I'm not going to do it here, just using that as an example. When we go from pi to 0, it's negative of the standard integral. So here's a bunch of rules. Here's the first one. The order matters. If we go from A to B, it's negative of from B to A. If we go from A to A, we haven't taken any area, of course, we're going to be 0. If we have some constant being multiplied, we just throw it out front. Negative applies. If it's a negative k value, -1 is k, you can throw the negative out front. If you have two functions, you can break them apart and do them separately, whether you are adding or subtracting. If you have from A to B and then from B to C, you can do it once from A to C. You get the same answer. And then some of the more complicated ones, a max min. This is actually fairly obvious when you think about it. Excuse me. Since the integral is an area, if we have a minimum, the area, I'll put this one in green, at the minimum, that's what this means, the minimum height times your B and your A, B minus A. This area is going to be less than the total area, to which most people say, well, duh. And if we have a maximum, and we draw the rectangle there, it's going to be more. And again, you would say, of course it is. But it's important to put it together because it's going to be used in the very near future. Domination. If a function is greater than another function all the way, then its integral is going to be greater, which is obvious. And that's this kind of thing. F of x, g of x. Nothing really shocking there. And if the function is greater than 0, then the integral will be greater than 0. So here's some examples. And the first few times people see them, they're a little bit like, what? And then after they play with them for a little bit, they're like, oh, okay, that makes sense. So we have the integral from 1 to 4 is -2. So from 4 to 1 is just 2. The integral from -1 to 4, well, we'll need to go from -1 to 1, and then from 1 to 4, add them together. And get 3. Now my screenshot's a little bit tight here, so I'll do the best I can. From -1 to 1, f of x is 5, so that's 2 times 5, plus 3 times h of x from -1 to 1 is 7. We get 31. That's here. From 0 to 1, we don't have any data. We don't know. So I don't even know if we'd say no solution as much as not enough information. And then if you look at the bottom ones, h of x from -2 to 2, I don't have anything there. I can't just double it. F of x and h of x from -1 to 4. Well, I know f of x, but I don't know h of x, so same thing applies. Got to know specific endpoints to the area. Otherwise, we cannot make a decision. So this is a classic, always with the trig when they're saying show that the value is less than, because cosine maxes out at 1. So there is no chance that 1 plus cosine of x is ever going to be greater than that. So if we were to graph it and say, well, I don't know what this looks like, but I know it's never going to get greater than the square root of 1 plus 1, square root of 2. So that's the absolute biggest it could get from 0 to 1. Look at that rectangle and we say, okay, that area is at most root 2, which is 1.414. This is 1.5. So we know that this will always be less than 1.5. I've actually seen this problem done a lot of different ways, but it's a good way to look at it. So, mean value theorem for derivatives. Something about if we have an a and a b, we have a slope between them. There's some c value. Really should have drawn that a little bit sharper, which also has that slope, parallel line. Why do we find it? And the answer is no idea. The better answer is used improving other things. And it's a little bit beyond my scope and the scope of this course, but we do use the mean value theorem for derivatives. We're going to create one for integrals, and we're going to use it to talk about continuous area. But it's kind of ludicrous. We're talking about average and stuff like that. So yes, we can use it to find the average of a continuous area. That's kind of crazy because average means add them up and then divide by however many there are. Well, in a continuous area, we don't know how many there are. It goes on and on and on and on forever. But doesn't mean we can't do it. We just divide by the endpoints. So find the average value, f of x equals 4 minus x squared on 0, 3. Now I'm actually going to jump here a little bit because, again, I don't want to use the calculator. We're looking for integral from 0 to 3 of 4 minus x squared dx. Oh, by the way, we're finding the average value, so it's 1 over 3 minus 0 times that. And this is going to pop up in a minute, so I'll show you how to do it. This is 1/3 antiderivative 4x minus x to the third from 0 to 3. We're not using this notation yet. I'm getting way ahead, but I would have just put this in a calculator and done a nint. But for now, we'll do it this way. The way that works is 4 times 3 is 12 minus 3 to the third is 27 minus, we put in 0, 4 times 0 minus 0 to the third. We get 12 minus 27 is negative 25. Something's bothering me here. Oh, I forgot the third. I did the antiderivative wrong. Okay. 12 minus 9 is 3. Divided by 3 is 1. So that's the average area. What does that mean? Well, let's do a quick graph here. Negative x squared plus 4 looks something like this. From 0 to 3 actually goes well below the line. So we're looking at this area and this area, and the average of this whole area is at 1, right about there. And we can find that point where it hits. We'll do that in a minute. So this is the mean value of the theorem. If f is continuous, then at some point C, oh, that's what I just said. At some point, we can find the average. The average, blah, 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 blah. So this one's talking about, hey, we find the average, and we find a point where that average exists. All right? So we're going to do that problem in a minute, but this is where we start to connect differential and integral calculus. The derivative of the integral is just a function. That's it right there. We're not going to prove it, but you're going to have to just take it. This is what I just did in the previous problem. I said if we're taking the integral of something from a to x, then we just say it's the antiderivative and we just assess it. So let's try a couple real quick. Antiderivative of sine is negative cosine of pi minus negative cosine of 0. That's negative 1 plus 1 equals 2. That just reminds me, way back at the beginning of my notes, I screwed that up. This is not 1, this is 2. 2 and negative 2. Sorry. That's why we do the math. Integral of 4x to the third, like I say, find the antiderivative, which is x to the 4th over 4. They cancel from negative 2 to 2, which is 16 minus 16, which is 0. And this is 4x from 0 to 5, which is just 20. And this is e to the 4x over 4. So take that derivative and make sure it makes sense. 0 to 1, which is just e to the 4th over 4 minus e to the 0, which is 1. And we could find a common denominator, but no need. So a lot there. We'll tighten this up next lesson. That's about it. Happy mathing.